In section 9.3, which is the only section we're going to do from chapter 9, we're going to combine definite integrals with area between two curves. And just a little bit of background information. If we had a function, say f of x, that went something like this, and this was from a to say b, and this area here would be considered positive area because the area is above the x-axis and it's trapped between the graph and the x-axis. This area here would be negative area because it's below the x-axis, and this little piece here would be positive. So if we call this piece 1, 2, and 3, if we were asked to find the integral from a to b of this function, it would really be whatever the area for region 1 is, minus the area of region 2 plus the area of region 3, and that would be your final definite integral. So area above the x-axis positive, area below the x-axis negative. What we're going to be looking at today is how do we find the area trapped between two curves. Okay, so if we take a look at this example, we have a linear function y equals x, and we have a parabola y equals x squared, and we are looking for the area of that shaded region. Okay, well, the first thing I need to do is I need to find my limits for my integrand, and my limits of my integrand are my intersection points. So the first thing I have to do is I have to find the intersection points. And to do that, we're going to equate the two functions. If y equals x, and if y equals x squared minus 2, then x has to equal x squared minus 2. And so now we're solving a quadratic equation. So we set that equation equal to 0. And I can factor to get x minus 2, x plus 1. So now using our zero product principle, I'm multiplying two things and getting 0. Either x minus 2 equals 0 or x plus 1 equals 0. So either x is 2 or x is negative 1. So therefore, to find the area, I'm going to put my lower limit negative 1 on the bottom, my upper limit positive 2 on top. Now, when you look at the shaded region, there is a curve that's on top of the shaded region, and that is the line of the function y equals x. The parabola is the bottom of the shaded region, so to find the net area, we take the top curve, which in this case is the function x, and we minus the bottom curve, which is x squared minus 2. So therefore, it would be the definite integral from negative 1 to 2. If I distribute, I get x minus x squared plus 2 dx. And now I'm back to what I did in section 8.4. I'm just evaluating a definite integral. But the answer to that definite integral is going to be the area bound by these two curves. So this is going to equal, if I integrate x, I get x squared over 2 minus the integral of x squared would be x cubed over 3. And the integral of 2 would be 2x. And my limits are going from negative 1 to 2. So now we plug our upper limit in, which is 2. So 2 squared over 2 minus 2 cubed over 3 plus 2 times 2. That's my upper limit. And then I subtract away whatever I get when I plug in my lower limit. So negative 1 squared over 2 minus negative 1 cubed over 3 plus 2 times negative 1. So working this part out, I get 2 squared is 4 over 2 is going to be 2 minus 8 over 3 plus 4 minus, this becomes positive 1/2. This becomes a negative 1/3 times a negative is a positive 1/3, and that becomes a negative 2. So now, if I distribute my negative sign here in the middle, 2 and 4 gives me 6 minus 8/3. So I've just collected like terms here. Distributing, I get negative 1/2 minus 1/3 plus 2. So this ends up being 6 and 2 is 8. So I basically combine the two constants. Negative 8/3 and negative 1/3 is negative 9/3, which is negative 3. And I still have this minus 1/2. So this becomes 8 minus 3, which is 5, minus 1/2. And if I was to get a common denominator, 5 would be 10 over 2 minus 1 over 2. My net area between the two curves would be 9/2, or 9 over 2. So that would be the area of the shaded region. So again, to review, we need to find the intersection points of the two curves, and then we look to see which curve is on top, and that's the function I put first, and then I minus the lower function in my integrand, and then I simplify it, and then do my process of definite integration. Okay, this next example, they're asking you to find the area of the region bound by this parabola on top and this parabola below, but these two graphs don't intersect like the first one, but they also give us two vertical lines. So they want the area from where x is -1 to where x is 2 trapped between these two curves. So again, to find that area, it would be the integral from -1 to 2 of the upper curve, which is x squared minus 2x plus 3, minus the lower curve, which is -1 minus x squared dx. So I am going to simplify this. So x squared minus 2x plus 3, that becomes plus 1 plus x squared dx, which becomes the integral from -1 to 2. I have 2x squared minus 2x plus 4 dx. And now I have to integrate this, plug in my upper limit, plug in my lower limit, and that would be my net area. So to do that, the integral of 2x squared is going to be 2x cubed over 3. The integral of -2x is -x squared, and the integral of 4 would be plus 4x, going from -1 to 2. So again, plug in my upper limit. And then plug in my lower limit, and watch your signs here, because it's a -1 that we're cubing. So this is going to be 2 cubed is 8 times 2 is 16 over 3 minus 4 plus 8. This will be -1/3 times 2, that's -2/3. -1 squared is 1 times that negative will be -1, and then subtract 4. This becomes 16 over 3 plus 4 when I combine these two. And then I'm going to distribute. Well, I'll just distribute in the next step. So this is still -2/3, -1, and -4 is -5. So 16 over 3 plus 4. If I distribute, I get +2/3 plus 5. 16/3 plus 2/3 is going to give me 18 over 3. 4 plus 5 is going to be 9. And if you want to combine those, I got 18 over 3. Oh, what am I doing? That's 18 over 3 is simply 6. Plus 9, or my net area is 15. So in this particular case, they did not give us, so we didn't have intersection points like in the first one. All we had to do was find, oh, where did I go here? We were given two vertical lines, and those vertical lines happen to be our limits. Okay, in our last example, if you notice in the last example, we have the function y equals x cubed and the linear function y equals x, and we're asked to find the area trapped between these two curves. And if you notice, in quadrant 3, the top curve is the cubic, the bottom curve is the linear function, but in quadrant 1, the top curve is the linear, the bottom is the cubic. So one way to set this up is to set up two different integrals, and before we do that, we need to find the 3 intersection points. So to do that, we're going to do the exact same thing that we did in the last question. We are going to equate x cubed and x. Now, one of the things people want to do is divide through by an x and get x squared equals 1, but then they lose one of their solutions. So when you're solving, you want to subtract the x over and make it equal 0. So if I factor an x out, I get x squared minus 1 equals 0. And now x squared minus 1 can be factored as a difference of squares. So therefore, I'm multiplying three things and getting 0. So either x is 0, or x is 1, or x is negative 1. So this x coordinate of that intersection point is negative 1. This one is 0, and this one here would be positive 1. So now to figure out the area, I'm going to set up the integral. And in this first integral, my limits are negative 1 to 0. My top curve is x cubed. My bottom curve is x. So that's going to give me the area of this first region. And then I'm going to add to that the limits from 0 to 1. And now my top curve is x, and my bottom curve is x cubed. So there you set up your two different definite integrals, and the first definite integral calculates the area of the quadrant, or area in quadrant 3 between the two curves, and the second integral calculates the area in quadrant 1. So let's go ahead and do the math now. So I'm going to integrate this integrand. So area is going to equal x to the 4 over 4 minus x squared over 2 from negative 1 to 0, plus, if I integrate this, I'm going to get x squared over 2 minus x to the 4th over 4 from 0 to 1. So plugging in the upper limit in this first case, I'm going to get 0. When I put 0 into both of them, it's going to be 0. Minus, now I'm going to put a negative 1 in. So I'm going to get negative 1 to the 4th power over 4 minus negative 1 squared over 2. Plus, when I plug in my 1, well, 1 squared over 2 is going to be 1/2 minus a quarter. So that's my upper limit. And when I plug in 0, I'm going to get 0 for my lower limit. So here, I end up with, and be careful with this negative sign, you get the negative of 1/4 minus, this will be positive 1/2, plus 1/2 minus 1/4. So if you work this out, I'm going to get, if I got a common denominator here, let's get a common denominator for all of these. 1/2 would be 2/4. Similar here, this would be 2/4. So I end up getting 1/4 minus 2/4 is negative 1/4. But if I multiply it by that negative 1, it becomes plus 1/4. And the second part, 2/4 minus a quarter is a quarter. So I end up getting 2/4. So my final answer is 1/2. So the net area trapped between these two curves would be 1/2 units squared. Okay, so that ends section 9.3, which basically ties together all of chapter 9 with our definite integration from chapter 8. So there's 3 questions for you to try on page 384, and that is the end of our supplemental learning. So you will be getting an assignment dealing with chapter 8 and chapter 9 coming out next week, and that assignment will be due on June the 20th. All right, good luck. If you have any questions, check the answers on the webpage or send me an email.